Hello there, everyone, and welcome back to another super interesting video on my channel. All right, so this time I'm going to be sharing with you a really interesting topic, and it's very similar to last time. In fact, you'll see how, remember how we went from arithmetic sequences to arithmetic series? Well, last time was geometric sequences, so this time, what do you think it is? Well, that's right, it's quadratic equations. No, I'm just kidding, I'm just kidding. It is geometric series. Haha. I totally fooled you. So, geometric series. Now, if you didn't get the idea of series so far, well, you might be wondering, why is it important? You have sequence. What's the point of having this too? Why would you ever need to sum up all the terms? I mean, I could just leave it with sequences. I mean, that would make my life easier, right? Well, I agree with you. My life would be easier, but my life wouldn't be easier at the same time. So, remember that mitosis example I showed you last time? Let's go back to that. So it's basically cell division. You start off with one cell, you make two, then each of those make two, each of those make two. Whoops. Yep. And this just keeps continuing. Now I would draw more, but I don't have space here, so yeah. Now, with geometric series, you could tell the number of cells after each division. So after the first division, you'd be here, and the number of cells would be 2. After the second division, after 2 divisions, you'd be here, and the number of cells is 4. So you could tell the number of cells after the end of every division. Now, what if you want to tell the total number of cells, including the original ones at the end of every division? So if we wanted that, basically what I'm asking you is, let me give you an example. If it was after 2 divisions, which would be right here, if I wanted the total population after those 2 divisions, that wouldn't just be 4, it would be 1 plus 2 plus 4. And that is 7. That's what I want to know. Now, this is with just 3 divisions here. It's very easy to just look back and count it. But what if I have, cell divisions? There are trillions and trillions of cells in your body. You don't have 7 cells in your body, and you can't count 1 trillion cells just sitting there. So instead, this is the reason we use geometric series, because after 3 divisions we'd sum up each term. Now you see how this relates? That's exactly why it's important. So if you remember in arithmetic series, the trick to solving that was flipping the entire thing around. In geometric series, there is a trick too, but it's not flipping the entire thing around. And here's one big misconception. Well, it's not a misconception, it's a mistake rather. And trust me, I've made this so many times. I just wanna, yeah, this mistake, it's super annoying when you make this mistake. You have to redo all your work. So the mistake is solving this like an arithmetic series. Let me start off with a geometric series, for example. 1, 2, 4, 8, 16. I'm just going with the mitosis example. So let's go to, actually, instead of writing this in numbers, I am just going to write in powers of 2, because it's the same thing. 2 squared, 2 cubed, 2 to the 4th. Now, if you notice, it's exactly the same thing. 2 to the power 0 is 1. This one's 2. 2 squared is 4. 2 cubed is 8. So it is the same pattern. I'm not changing any of the values here, just writing them differently. And let's say it goes up to 2 to the power 20. Now, when you write in exponents, it's much easier to go up to very high powers, because all you have to do is write the exponent, and you don't have to actually expand it out and write it fully. So yeah, that's one. So if we were to write the sum as s, now, if you remember in arithmetic series, when we flip it, we just simply write s, and we would redo 2 to the power 20 plus 19 plus 18, 17, 16, this way. Now, you might be thinking, aha, this actually works. Look, the exponents add up to 20 each time. Well, the numbers are in the exponent. So when you add exponents, you cannot, when you add two numbers raised to power, for example, 2 squared plus 2 to the power 18, you cannot add their exponents. This is not equal to 2 to the power 20. That's not true. Only when you multiply them, it's equal to 2 to the power 20. So 2 squared times 2 to the power 18 is equal to 2 to the power 20. Now, if you're thinking, why don't you just multiply this then? Multiplication on addition works very differently. If I multiply this, I have to multiply this by that, each of these terms by every single term, then this one by all the terms and the entire thing, and it'd be a just huge mess of like 100 terms or something. I don't even want to count it. Yeah, so flipping does not work. Instead, what you do is multiply the entire thing by the common ratio. And in this case, the common ratio is 2. So you say 2s is equal to 2 to the power 0. Now, I could write 2 to the power 1 here, because 2 to the power 0 times 2 is 2 to the power 1. But instead, I'll write it under the other 2 to the power 1 to make it look nicer. So now this is our series. And now here comes the second biggest mistake that even I made so many times, I can't count it. And I wouldn't count it even if I could. That's a different thing. But people just stop here. You just stop here. I've just stopped here. But notice if we multiply each of this, it would start off at 2 to the power 1 and go to 2 to the power 21 because we're raising each of those. So just stopping at 20 would give you an inaccurate result. Therefore, you have to remember to include that last term. Don't forget that. Remember that. Then you see that all these terms are pairs of equality. Now we got something nice. So if we add them, you're just going to double them up. Instead, you want to subtract to cancel. So if I subtract the two equations, I'll end up with this. Now, as you can see, this first term has nothing to cancel with. So s minus 2s is negative s. Let's just get that out of the way. This first term cannot cancel with anything. So 2 to the power 0 minus 0 here, that's just 2 to the power 0. Now, this this 2 to the power 21 here cannot cancel with anything. So this 2 to the power 21 has nothing to cancel it. In fact, it's just a 0 there. So 0 minus 2 to the power 21 is negative 2 to the power 21. So all the terms cancel except for the first term of the first equation and the last term of the last equation. That's pretty neat. And then all you're doing is multiplying or dividing both sides by negative 1. And instead of writing 2 to the power 0, I'm going to write the actual 1 now. 1 minus 2 to the power 21 over negative 1. Or you can flip the thing in the numerator and just write as 2 to the power 21 minus 1. And there you go. That's your answer. No, I am not going to expand this out. If you want, you can use a calculator to do that. But yeah, that's all that's important. Okay. So it turns out that it's very neat to solve any of these problems. It's actually very fun too, and you keep doing it. So now let's do a generalized one. Since I'm sure you guys can all do this, just rewatch it. So like if you had 1, 3, 9, this time the common ratio is 3. So when you had to add up all those 1, 3, 9, and if you had to go up to, let's say, uh, one sec, I am going to calculate 3 to the power 10, and that is, well, I'm not even going to say that, but I'm just writing here, 59049. Okay, I said it, whatever. If I wanted to go up to there, that's 3 to the power 10. I'm going to use the same logic by multiplying it by the common ratio. Remember, multiply by the common ratio. Don't multiply by 2 for everything. That's not the common ratio in every series. So here's 3s, and then 3, 9, blah, 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 blah. So yeah, same technique. Now, if you were to generalize this, let's say you started off at ar squared, or whoops, ar squared, ar cubed, ar to the nth. Excuse me. Now, like before, I'll just let this be s. I'm just going to change color in between here. Yeah. The common ratio is r. So this time it's rs is equal to AR plus AR squared plus AR cubed plus AR to the nth plus, remember this last term, AR to the, whoops, why do I keep doing that? N plus 1. Right, now we just subtract like before. Excuse me again. Now, if these variables look different from numbers, and they are, don't let them scare you. Just pretend they're numbers. If you're really confused by the variables, just plug in a value for A, let's say 1 and R 5, and solve and see how it goes, and then try to do the variables. Don't let them scare you. They're not scary. They're babies. So S minus RS. Now this, if you factor out the S, it'll just become 1 minus R S, and I'm just gonna, now we can subtract this. You can see these pairs cancel all the way to here. There's a bunch of canceling that takes place here. So the first minus last. And you'll have A minus AR to the power n plus 1. After this, to isolate that S, you want to divide by 1 minus R on both sides. And doing that will give you A minus AR to the n plus 1 power over 1 minus R. Or this is actually more commonly written as A into 1 minus R to the n plus 1 over 1 minus R. I just factored out an A from the numerator. Now, this is a neat trick when you generalize numbers with variables. When you do it with variables, you get a formula for all numbers because a variable could stand for anything. So this is your formula for a geometric series. It's not very neat, I know, but the point here is don't memorize this formula. If you memorize this formula, you're never going to be able to solve this nicely. Understand how you get the formula, and it'll be very easy to solve. Now I'm going to move on to something interesting. Imagine if we were going back to arithmetic series. What is this sum? 1 plus 2 plus 3 plus 4. It looks simple so far, but infinity. On to infinity. Infinitely this will continue. What is this sum? Well, this is definitely undefined. It does not have a value. Well, at least there's a huge debate going on about this in the mathematical world, and people are finding all kinds of proofs to find this value. However, the basic assumption is that this has no value. It's undefined. Now, there are certain complicated formulas from which you find answers like -1/12. What? Well, yeah, if this doesn't make sense, don't worry about it. This doesn't make sense to me much either. Well, I don't understand how it's possible because 1 is 1, then 1 plus 2 is 3, 1 plus 2 plus 3 is 6, and it just keeps increasing. It's an increase in value as you keep going. So there's no way it can go to negatives. Yeah, so that's how I view this. But in geometry, the geometric series, it works differently. I'm going to use a classic example here. So I were to do 1 plus 1/2 plus 1/4. Excuse me. Now, just this series, I'm going to continue it infinitely this time. Here, the common ratio is 1/2, or 2 to the power -1, whatever. Interestingly enough, this does have a sum. Wow, could you believe that? Well, let me show you. 2s, oh sorry, 1/2 s. Multiplying by the common ratio here, then you'll get 1/2. 1/4, 1/8, 1/16, and so on. Now, since there is no last term, this sum won't have a last term either. So when it comes to an infinite series, things cancel out much better. Only the first term remains, and every single thing after that goes bye-bye. So s minus 1/2 s, or 1/2 s, is 1. Then that means s is equal to 2. Whoa, we actually found a value, and it's actually surprisingly simple. 2? That's actually insane. Now, of course, with all this algebra, you won't really understand, and I didn't understand too at first why this is true. But with a nice geometric interpretation, let's see why. I'm going to draw 2 rectangular blocks here, and hopefully this example will help you see a better interpretation of this. Right. All right. Okay. Now, you're starting off at 1 here. Let me switch colors. 1. Whoops. You're starting off at 1 here, which means you're claiming the entire first block. This is 1. Then half is half of the second block. So I'm claiming half of this. Then 1/4 is 1/4 of the second block, or half of the block. So half of the remaining. And see, this is where the common ratio comes in. Now you can see how 1/8 would we split this into half and claim 1/4. Now you can really see the common ratio kicking in here, right? Split it in half again and claim this, it's 1/16. Split it in half, and it's 1/32. Split, 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 split. Now, am I ever going to actually touch this outer? Excuse me. After 20 times, will I ever touch 2? No. After 30 times, will I ever touch 2? No. After 100 times, will I ever touch 2? No. After 1,250,000,000 times, will I touch 2? No. But if you go infinitely, like forever, again, the concept of infinity is really hard to grasp, and I struggled at it so much at first too. But if you go forever, infinity, then infinitely many distances away you'll touch 2. That's how this idea is. Now, this only works if the common ratio is in between -1 and 1. All right, time to generalize. Let's say you have AR, AR squared, AR cubed. Oh, let me change these to plus signs. There we go. To the 4th, and we'll keep going forever. Let that be S, then you'll have AS is AR, AR squared, AR cubed, AR4, then even this continues forever. Subtracting, you have 1 minus AS is equal to, whoops, one mistake here, this is R, not A. Then S is equal to A over 1 minus R. Now look at how simple this formula is compared to that of a finite series where you can actually see the n term. It's very simple. A is the first term, R is the common ratio, and that's all you need to find the sum of any given series now. This is important. This condition needs to be met always, otherwise the series the infinite series would have a sum. All right, that's it for this video. I hope you enjoyed it. Please subscribe to my channel and hit the like button and be on the lookout for new and interesting videos. Thank you for watching and see you next time.